So today we're going to investigate exponential growth and decay. And we're going to start with a paper folding activity. And we're going to have to fill out the chart along with this. So let's look down on our papers at the chart to start off. And so first of all, what I just gave you, again, just a piece of scrap paper. And it says, take a regular sheet of paper, and we're going to be folding it in half. But first of all, when we have just the regular sheet of paper, how many sections of this paper do we have? Well, we have one. We've got one piece of paper, and then it says area of each section compared to the original paper. Well, we haven't done anything to the paper yet, so we're going to have one there. But now we can follow the directions. And the directions say, take a regular sheet of paper and fold it in half. Gonna fold it in half. You can fold it hot dog style. You can fold it hamburger style. It doesn't make any difference. Now, what we have is we have two equal sections, each with an area that is half the original area. So now, if you look at our chart over here, it says number of sections. Well, we've got two sections now. And our bottom category says area of each section compared to the original paper. Well, now each section is half as big as our original piece of paper. So let's fold that back up. You don't have to be super meticulous about it. And then we're going to do it again. So we're going to fold the paper in half again. So we're going to fold it. When we unfold the paper, how many sections do we have now? We've got 4. And the area of the section compared to the original paper is 1/4. We're looking at each square here, so here's a square, here's a square, here's a square, here's a square. So let's fold it back up. And then let's put another fold in it. This is our third fold. You don't have to be super compulsive about it. When we unfold this time, how many sections do we have? We have 8. And what's the area of one of these sections compared to our original piece of paper? Excellent. And you're probably starting to see the pattern here, but we'll fold it back up. And we're going to put a 4th fold in it. And when we unfold, again, some of you probably see the pattern already. How many sections do we have? We actually should have 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So what's our area of each section compared back to the original? 116. So we'll fold that back up, and one more time. It's starting to get difficult. Again, you don't have to be super precise on this. You can get the idea of it because it's starting to get hard to fold. But how many sections do you think we've got? 32. And if you're looking at the pattern, you can probably see that the area of each section compared to our original is going to be 1/32. So there's our paper there. If we look here now at problem number 4, or part number 4, it says recall that the definition of a function says that there is exactly one output value for each input value. That's the definition of a function. So if we look at this one, the relationship between the number of folds and the number of sections is a function. And why? Well, there is exactly one output, which in this one we're comparing the number of sections. So our output is going to be the section. There's exactly one output, the section. When we, how to say this? For our input, which are the folds. There's exactly one output. Each time we folded, we got a different value for the number of sections. What is the domain of this? Well, if you can't quite tell, problem C or part C might be helpful for us. But the domain for this function is the folds. And in general, remember that domain is considered to be an x value. And that's why I say part C might be helpful, because it says on the axis to the right, let the horizontal axis represent the number of folds, let the vertical axis represent the number of sections. And we're going to take our values here and we're going to plot these on our paper. So what we've got here, if we look at our table, we started off with 0, 1. And as I flip back here to the table, 0, 1 is the first value that we're doing number of folds and number of sections. So then we're going to go to 1, 2. 1, 2. Our next value on the table is 2, 4. Then we get 3, 8. 4, 16. And then our 5, 32 doesn't fit on the graph. But the question is, does it make sense to connect the points with a smooth curve? And it doesn't. Think about what you're working with. It doesn't make sense to connect, because if we connected, that would be saying that we have parts of sections, and we don't have parts of sections. So no, there are no partial. Set that up so you can see it. No, because there are no partial sections. We've got folds, and we've got the sections. We don't get pieces of that. So if you think back to yesterday here, if we look at our chart, remember yesterday we had a similar chart, and we had things like this in it. We multiplied by 2, and we multiplied by 2, and we multiplied by 2, and we multiplied by 2. In fact, we said we could go the other direction where we would be dividing, but ultimately we multiplied by 2. Hopefully you remember that from our notes yesterday. Because what we're going to do is we're going to write a function for this. And our function for this is going to be f of x equals, well, we're multiplying everything by 2. And in fact, it's going to be 2 to the x. And once we determine what the value for a function is, then we can go back here and we can figure out, well, how many sections will we have after 15 folds? So this is going to be f of 15. And we're going to put that value of 15 back into a function wherever we see x. So that 15, like I said, is going to go back in here for x. So it's going to be 2 to the 15. There's. It says how many sections would you have after 15 folds? And that's not one that I'm expecting you to memorize, nor would I. So we go back into our calculators, 2 to the 15. And we get 32,768. So we get a lot. And that's just with 15 folds. And it would be really hard to fold those. On your paper, I think that part of it got copied here for part G at the bottom of your paper, and if not, then it should be on the other side of your paper. And it says the function f that you found on the front of the sheet is an example of an exponential growth function. What do you notice about the equation, the table, and the graph of the function? Well, without spending a lot of time here, I went back and I looked at this. And the first thing that stood out to me was that this is not linear. It's not a linear function, which is what we said at the first thing with our notes yesterday. And then if we're really looking, again, I'm specifically looking at the graph. But coming from the left on the graph, all of our values continue to get larger, which means that this is an increasing, look, might be nice, increasing function. And a couple other things that you may or may not have noticed is that we have a y-intercept on this graph. Where does the graph cross the y-axis? It crosses at 0, 1. But if we're really looking at this picture, what we also see is that we don't have an x-intercept. We never touch the x-axis. So those are a couple things that I noticed. You may have noticed some different pieces there of the graph or some different characteristics. But that's an exponential growth function. So if we continue to look at our table, and I'm really sorry I should have copied these on separate papers. Now what we're going to look at is we're going to look at the number of folds and the area. So it's easy for me to flip back here, or maybe easier. So now we're going to look at the number of folds and the area back here in our table. And it says, explain why this is a function. I am going to write the answer to A here, just to give myself a little bit more space. But once again, remember that we're looking at the relationship between outputs and inputs. And the answer is really close to the same that we put on the front. There is exactly a C, exactly one output. But this time our output happens to be the area of the section of the function. There's exactly one output for each input, and our input is still the same. It's the number of folds that we're working with. So I just put that there where I have a little bit more space. I think you have enough space on your paper. I couldn't get it quite in there earlier. So that's the answer to 5A. It says, what's the domain of this function? Well, our domain is still the same. It's going to be the folds. And now what we want to do is we want to draw the picture with the folds and the area in it. But we need to label our graph a little bit before we get there. So on our x-axis, I just did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then on the vertical, it says, let the vertical axis represent the area of each section. Label the y-axis by 0.1. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. And I know I didn't put them all in there. It's hard to squeeze that in, but here's 0.6 and so forth. So where am I getting these numbers again? From the table in the front of the paper. And we're starting with number of folds is 0. And then our area of the paper was 1. So the top part of our chart and the bottom part of our chart. Then when we had 1 fold, we had 1/2, and that is 0.5. And let me digress for a minute here. If we go back to the chart, where am I getting that number? Well, I did 0, 1. So this is going to be 1, 1/2, which is 0.5. And it's going to be 2, 1/4, which is 0.25. And it's 3, 1/8, which is 0.125. And it's 4, 1/16, which is 0.0625. And I don't remember what 1/32 is, but 1 divided by 32 is 0.03125. And that's what I'm graphing. I'm going to go 2.25 and 3.125. So now that we've got the decimals back in there, that'll be a little bit more helpful. Again, 2.25. Somewhere in here. 3 folds gives us 0.125. 4 folds gives us 0.0625. Somewhere in here. And 5 folds is 0.03 something, so it's roughly here. And do we want to connect these values? We're comparing folds and area. Do we ever have a partial area? We don't ever have a partial area. So once again, no. Because there are no partial areas. But if you think about this too, what we're looking at here is we're looking at the folds compared to the area, and we want to write the function. Well, if we think about it on the front, we did f of x equals 2 to the x. But what we're really looking at is we're coming up with these values. This 1, 1/2, 1/4, 1/8, 1/16, 1/32. What can we do to our function so that we end up with a fraction? What's going to cause us to get a fraction? Somebody said it. Yep. And it's going to actually be, 2 to the negative x. Now, if you prefer, if you don't like that negative x, then the other way to write this, remember, is that this would become 1/2 to the x. So once we determine whichever function we need, then we can use this function to determine the area of the section when we have folded 15 times. So we get f of 15 equals 2 to the negative x. We're going to take this value of 15 and we're going to put it back into our function wherever we see x. And we get 2 to the negative 15. Again, not something that we're expecting us to know. If we type that in our calculator, 2 to the negative 15 gives us that. Which means nothing. It's, by the way, in scientific notation. But if we use our other formula there, where this is going to be 1 divided by 2 to the 15th, because we flipped and changed the sign on our exponent, then maybe what's a little bit better is the fact that 2 to the 15th was 32,768, which we found earlier. That's going to be the area of it. So I'm going to skip G here for a minute and flip down to the very bottom here. You can probably guess what I would put in the G. But I want to look here to wrap it up. And if we can make some inferences about our function, well, our function, an exponential function, is in the format of y equals b to the x. Well, in terms of a growth equation, our base, our b, is going to be greater than 1. But when it's decay here, our base is going to be between 0 and 1. Because remember what we just did a moment ago, we did the fraction, we turned it into 1 over 2 to the 15th. So our base would be between 0 and 1. As I go back here and just fill in this last part here, I wanted to not run out of time on that last part. This function g, when we go back and look at the picture, it's an example of exponential decay. Well, if we look at the graph, decay goes with decreasing. We started high and we got lower. This is a decreasing function. When we go back and look at our y-intercept, we still have a y-intercept of 0, 1. And if you look really close at the picture, just like the earlier graph, we do not have an x-intercept.